Well, if VD can vary across an element and the current doesn't change through it and the current is zero, then that's an open circuit. So in this case, it behaves like a resistor, and in this case, the device behaves like an open circuit. All right. So continuing with the example, supposing I build a little circuit that looks like this with a voltage and resistor. This is my usual Thevenin trick. And if I go ahead and build this for you, let's take a quick look at how would I go and solve the circuit if I replace my nonlinear device with a linear approximation, where the linear approximation is an open circuit on the left-hand side and then a resistor on the right-hand side. Supposing I am told that V is positive. Okay, so what I'm trying to do here is figure out for the circuit that I've shown you here, for this circuit, I'm trying to figure out which of these two elements apply, whether it's region A or region B. Now, supposing we are given that V is positive. If V is positive, what does that mean? If V is positive, notice that, I have two segments here. One of them is an open circuit, one of them is a resistor. And so in this case, if I'm given that V is positive, then I'm going to have a positive voltage here. And if I have a positive voltage here, then I'm going to be in the right-hand part of this figure, and so linear region B will apply. Okay, so if V is positive, then D will operate in linear region B. And so if D operates in linear region B, then I can replace D in the circuit with the resistance of value 1 by R when D operates in linear region B. So let me just make it 1 by RD to distinguish it from the other resistance. So if the slope of this line here is 1 divided by RD, then I can replace the device with a resistance 1 divided by RD for the purposes of calculating parameters related to the circuit when D operates in this region. So what that means is that in region B, my equivalent circuit will look like this. I have my voltage source as usual at the resistance R, and then I have a resistance at this point, RD. Okay, so this is VD and this is ID. So what that says is if V is positive, if the source voltage V is positive, then my nonlinear device will operate in linear region B, where it works like a resistor with resistance RD, and so I can replace a nonlinear device with the resistance RD. Now, it generally is quite a trick to figure out what is the right set of approximations to make when you have circuits like this. And so, that is somewhat of an art form, and so, practice certainly helps with that. But you may also have a piecewise linear device to begin with. So if someone invents a new device that has some characteristic that, for instance, looks like this. Okay, so this device is piecewise linear. This is VD and this is ID. And if this device has a piecewise linear relationship like that, then that may be a set of device properties that comes from the device itself and not from any approximation. Either way, whether the device that you're given itself is a piecewise linear device, or whether you've taken a nonlinear curve, for example, some nonlinear curve that looks like this, and if I replace that curve with a piecewise linear function that looks like this, then I can go ahead and use those regions and go and solve my circuit. And as before, I have to first figure out in which region the device is operating for a given set of values of the other parameters in the circuit. And then I can go and replace that device with the appropriate resistance value. So for example, if I had this device, then this is one resistance RA, and this is some other resistance RB. Okay, so I would replace it with the appropriate resistance and then compute the appropriate solve the appropriate set of equations, which would all be linear, because in the piecewise linear method, I'm actually solving a linear circuit in that region of operation.